What's up, AP Physics students? Today we're going to be talking about applying our basic understanding of circular motion onto a couple problems that if we're given, we can apply that knowledge we've ascertained about circular motion and then hopefully better understand it in real life situations. So without further ado, let's get started. So let's get a problem up in here. So we have a child, and he is sitting 1.20 meters away, or 1.20 meters away from the center of a merry-go-round. He is traveling at a speed. He's traveling at a speed of 1.10 meters per second, and his mass is 22.5 kilograms. So with all this given information, we are asked to calculate his centripetal acceleration, which I'm just going to shorthand name it as AR, which is another way to say centripetal acceleration, and his net horizontal force, or the net horizontal force acting on this kid. So rule number one of physics: whenever you're given a problem, try to draw out a quick diagram so that maybe you can derive certain equations or better picture the problem that you're given. All right, so let's try to draw this merry-go-round. Now, usually we know if we are just looking at a merry-go-round, if we're standing on the ground and watching a merry-go-round spin, we're looking at it from a side view. So I'm going to do my best to kind of give a side view, but ultimately we are going to be looking at it from a top view. So we have this circular merry-go-round, or an attempt to make it circular, and we have a kid at one end of the merry-go-round, and the center, let's say hypothetically, is here. And the problem states that this kid is 1.20 meters away from the center of the merry-go-round. So we can draw this. So the distance between this kid and the center is 1.20 meters. And we know that this kid, if he was turning in this direction, the merry-go-round is turning in this direction, we know that his speed would be, or his tangential velocity would be, as the problem gives it, 1.10 meters per second. All right, so they give us two pieces of information which I drew on to our diagram. All right, and this kid's weight, or this kid's mass, his mass is 22.5 kilograms. All right, 22.5 kilograms. So we drew all the information onto our diagram. And now we're left with calculating. So the first thing we have to calculate is his centripetal acceleration. Now, if we know from the basic understanding we have of circular motion, and if you are kind of, forgetting it, if you're kind of a little, confused on some of the basic principles of circular motion, please do look at an earlier video, but I'm going to assume that you know it, and that's why you're here on applying circular motion. So we know that the formula for centripetal force is our tangential velocity squared over our radius. All right? So our centripetal acceleration, well, what information have they given us? Well, they've given us our tangential velocity, and they've also given us our radius, because it tells us from one end to the center, and that's nothing but your radius. It's half the distance of the circle. So we'll plug those values in. So our centripetal, or our tangential velocity is 1.10 meters per second, and we have to square this value. And our radius is 1.20 meters. So if we were to put this into our calculator, we would get the value of 1.008 meters per second squared, but because we have sig figs here, we can write it as 1.01 meters per second squared, as his centripetal acceleration. And that looks like a D. I'm sorry. Centripetal acceleration. Here we go. So this would be our answer for centripetal acceleration. Once again, if you're confused about, wait, where the heck did you get this equation from? Please look at a previous video that I've made on the basic principles and characteristics of circular motion, where I explain not only centripetal acceleration, but I also explain the net force and how we would be able to look at that. All right, so now let's solve part B of our question, which is find the net force acting, or the net horizontal force acting on this child. So another way you can write net horizontal force, well, you can write it as F net, but I usually write it as the summation of all the forces acting on it, and this R implies that we have centripetal acceleration, which you'll see in a short bit. So when I use this type of nomenclature, what I really mean is F net. All right, so we know that this F net, this horizontal force, is equal to some radially inward force. All right, some radially inward force. Okay, so, and if you don't understand why, please do look at the previous video. So we know that it's equal to some radially inward force. All right, we can simplify this into, or the summation of all the forces acting on this kid, we can simplify it as mass times our centripetal acceleration. And that's basically Newton's second law. The net force is equal to mass times acceleration. So all we did was we simplified this net force into mass times our centripetal acceleration. Nothing but Newton's second law and basic dynamics that we already covered in chapter 4. And it's equal to this radially inward net force, this radially inward net horizontal force. So what information are we given here? Well, we're given his mass. His mass is 22.5 kilograms, so we can plug that in, 22.5 kilograms. And his centripetal acceleration, we already calculated his centripetal acceleration right here, so we can just plug in that value. 1.01 meters per second squared equals this radially inward net horizontal force. So if we type this into our calculator, we get 22.7 newtons equals this radially inward force, or this net horizontal force acting on this kid. So this would be our answer to part B.